Alrighty, nerds. Today, Unit 1.4, most of Unit 1.4a. We won't get to all of it. So I guess, like I said, this will be a 3-day video. Talking about polynomial functions, and we're still talking about rates of change. So we're going to walk away from quadratics and straight lines and move into spaghetti graphs. Yay, polynomials. You should have spent a considerable amount of time learning about polynomials in Algebra 2. A lot of polynomials. So in this lesson, we're going to identify some key characteristics of polynomial functions related to rates of change. It says we can identify intervals over which the function is changing in very specific ways. And those ways are nothing new. You've done them in Algebra 2, and then this year it's going to be positive, negative, usually not positive, negative, focusing more on increasing, decreasing with concavity. So increasing, decreasing, concavity, intervals. In the previous lesson, we explored this behavior of increasing, decreasing, and constant functions with relationship to straight lines and quadratics, and now spaghetti, okay? In case you don't remember what a polynomial is, I'm going to too long didn't read it. A polynomial is a string of objects that are held together with pluses and minuses. And these objects have variables. Those variables' exponents must be whole positive numbers. So no decimal exponents, no fractional exponents, no negative exponents. That means no x's in the bottom of fractions. Held together with pluses and minuses, it's called a polynomial, and each of these things that's between the pluses and minuses is called a term. It's not here, but standard form of a polynomial writes it in order from biggest exponent down to smallest exponent and possibly no exponent. That's standard form. Why do we care? Because when it's written in standard form, that first term gives us a lot of information. Firstly, the biggest exponent, that is the degree of the polynomial. So x to the 5th graph with all kinds of other x stuff, that's a 5th degree polynomial. Quadratics, second degree polynomials. The number that sits in front of the variable with the biggest exponent is called the leading coefficient. The leading coefficient is important to us because it'll often tell us some information about the end behavior, which way the endings are pointing and stuff like that. You should remember that kind of stuff from Algebra 2. Turning point, I can't remember if we actually coined this term yet or not, but a turning point is a place where the function changes direction. So you stop going up and start going down, or stop going down, start going up. Essentially, swapping between increasing and decreasing. It's called a turning point. And in behavior, that just means what's the graph doing to the far left and to the far right. That'll come up more later on in the unit. Okay. Let's talk about extreme values, extrema, maxima, and minima. These just mean tops of bumps and bottoms of bumps. Tops of hills, bottoms of valleys. We call them extreme values or maxima or minima. For any function, what was that? I just lost my brain. Where'd it go? Okay, so for any function f, if there exists any interval from one x to another x that contains a value, as long as that value is, how do I want to say this? As long as your x value is not the one we're looking at, these things are true. But it's so confusing with those kinds of symbols. You know what this really is all telling you? It's really telling you it's called a local maximum if this y value is higher than the y values immediately around it. That's what that says. Because remember, it says as long as x isn't b, if f of b is bigger than all the other f of x, that's just a fancy way of saying this y value is bigger than the ones that sit immediately around it.
How close is the range of immediate?
That's a good question. How close is the range of immediately? Like immediate. Like right. Okay? Because we're not going to be dealing with flat zones. There won't be intervals of flat. So it'll be obvious. Oh, it's the top of a bump or it's the bottom of a bump. Okay? It's the top of a hill, bottom of a valley. We can call local maximums, which, you know what? Let's just go ahead and write max on these two. this is a max, and this is a max. I have a max in this classroom, actually. Anyway, these are maximums. They can be called local maximums. They can also be called relative maximums, because it's a maximum relative to the points immediately around it. It's a maximum in its local neighborhood. And the bottoms, valleys, will be called minimums. This is a local minimum, also known as a relative minimum, for the exact same reasons. That doesn't mean it's the highest on the graph. That doesn't mean it's the lowest on the graph. It just means it's a highish point. What I like to, when I was talking about this stuff to Algebra 2 this year, I said, imagine it rains. Imagine it rains. Anywhere where water would puddle is a minimum. And anywhere where water would wash away from because of gravity is a maximum. Cool? We call them local extrema, or you could just say extrema. You don't have to say the word local if you don't want to. I've never seen this word used before other than in notes. A singular extreme value is called an extremum. Never used that. And you could say local or relative. It doesn't matter. They mean the exact same thing. And you need to be comfortable knowing that they mean the same thing in case they show up on a test and they're used both ways. It says on this graph to the right, we're going to do some coloring. We need a red and we need a green. Okay? It says shade increasing in green, shade decreasing in red. If you don't have colored objects, by all means, just write INC next to the graph where it's increasing and DEC next to the graph where it's decreasing. Okay? Don't need to bend out of shape if you don't have the colors. Increasing was green. This far left-hand side of the graph is increasing. Remember what that means. As you go from left to right, your y values are getting larger. That is increasing. You're also increasing after x equals 2. As you go from left to right, your y values are getting larger, increasing. And in between them will be the only zone where we're decreasing. Decreasing official definition, as you're going from left to right, your y values are getting smaller. Another way of saying that is they are getting larger in magnitude as you go more negative, but they're getting smaller. And we were supposed to write these zones as intervals. So in green for increasing. Far left is negative infinity. And we stop increasing at the x value of negative 1. We are increasing again, though, later on, so union. Oh, AP wants brackets on change between increasing and decreasing. Sorry, my calculus knowledge jumped in there and said that doesn't make any sense, but we're going to do it anyway. We will be increasing again after the x value of 2. But we'll never stop increasing after that. However, we are decreasing between these two x values, so we'll decrease, and make sure you use brackets, from negative 1 to positive 2. Someone last period said, so when you're doing your intervals for increasing, decreasing, you don't care about the y values? And I said, actually, you never care about the y values unless you're talking about the range. Intervals are always going to be x values unless you're talking about the range, because you're describing where you see a certain behavior. Where is always the input values, the x. Now, if I said, where is a maximum? There's one here. Where is a minimum? There's one here. At x equals negative 6, there is a maximum. At x equals positive 2, there is a minimum. If you said, what is the maximum? The local maximum has a value of 6. The local minimum has a value of negative 6. So the where is something occurring is an x, an input, and the what is that value is a y. So where is x, what is y? Comfortable with that? Okay. By the way, part C just said to label it. I just did it. Questions, comments, concerns about increasing, decreasing, local max, local minimum? Yes?
So for max and minimum, I'm just sort of checking. If it says where is the max and minimum, you would say -1, -2?
Yeah, if you said where is the local maximum, at x equals -1. You'd have to say x equals. So yeah, but when you say where, x is the answer they're looking for, but you would need to say x equals. Now, unless it said at what x value does a minimum occur, then you go, oh, 2. Because they already said at what x.
So, oh, okay. So why do you have to?
Yeah.
Okay.
I believe on the next page we have more vocab. Oh, no! On the next page, we get to learn some graphing calculator stuff. This is going to take a little while. Use a graphing utility. Hello! To determine the relative maximum and minimum of this function right here. Then state the intervals where the function is increasing and decreasing. And then after we've done that, we want to know the connection between relative extrema and the intervals for increasing, decreasing. On is on the bottom left-hand side. Doink. Okay. So you turn your calculator on. If you would like to graph a function, you click on y equals. Boink. And it'll go here. If, for some reason, you've used this graphing calculator in the past or you bought a used one, if any of these things up top is highlighted, plot 1, 2, 3, if they're highlighted, scroll up and click enter to unhighlight it. Otherwise, it's going to throw an error. You should not have any plots highlighted right now. Okay. So if you've taken Prob and Stats and used this calculator before, it might be like that right now on your calculator. Anyway, we're going to type this in exactly as we see it. Negative is right here. Do not use the minus sign. If ever you use a minus sign on the front when it should have been negative, it will say syntax error. Essentially, if you see syntax error, that means you used a negative symbol when you should have used a minus. Yes, ma'am, what's up?
I think I used this before.
Mm-hmm. Refresh, what do you mean? Just press up if one of these things is highlighted, and then press enter, and it'll unhighlight it. Okay, so -2. This is your button for variable, right here next to alpha, x. Raised to the 5th power, you're going to have to use this caret symbol to get exponents that are other than 2. Raised to the 5. You press the right arrow to get back down to where you would type normal stuff. Plus 10x. Since that is x squared, you could use the caret symbol again and type 2, or you could just use the squared button. There is a squared button right there above log. Plus 16x. I'm going to press zoom 6 because that's going to take me to the standard window of 10 in all 4 directions. If I know for a fact that I already had the standard zoom on, then I could have just hit the graph button. So why didn't I just hit the graph button to find out? Because when you're taking a timed test, the last thing you want to do is waste time watching it graph something that has a bad window. If ever you're stuck and it'll have this little yellow circle up here spinning while it's thinking its way through graphs, and you know it's going to be a bad graph and you need it to stop immediately, try to shut the calculator off with second on. That's the same thing as Control-Alt-Delete. It'll kill the process, just so you know. Anyway, as you can see, my window was not appropriate, was it? I mean, I didn't need to go all the way out to -10 on the x. I need to go all the way out to +10 on the x. My negative y's are fine. I did capture the bottom, but you could see I didn't capture the top. So we need to change our window. This is the window button. You will notice my x min and max say -10, +10. Same thing for the y min and max with a scale of 1, meaning it's counting by ones. My x minimum did not need to go as far left as -5, did it? I just hit graph. Or as -10. So just to get a better graph, I'm going to take it to say -5. And instead of going to +10, I'm going to go to 5. -5, make sure that the 0 is not still there. Oh, wait. That one? That's what I meant. There. Scale. I mean, it can count by ones. That's fine. 1, 2, 3, 4, 5. That's fine. -10 was a good number on the y-axis. I could see that minimum there, right? But I couldn't see the maximum. Would anybody like to take a stab at how far up we should go? He says 50. David, is it because you already tested 50?
Yes.
Oh, see, he cheated. Okay. In period 7, someone said 20. Well, my experience told me 20 wasn't going to be enough. How'd I know? Because I saw that maximum had a really steep bump. So I took it to 20 for him. And then you see, oh, sometimes you weren't right. So if you're not right, it's not a big deal. Go back to window button and change the maximum. And I happen to know from last period, and because I saw 20 fail, I then told them, let's go scorched earth and go to 50. Don't creep up by 10 at a time. You're probably going to waste your time. Take bigger jumps than that if you're trying to get to big Y values. Now, as far as the scale is concerned, it's going to go down to 10 and up to 50. And I don't want to see 60 tick marks. And that's what it's going to give me right now. The reason why I don't want to see 60 tick marks is because it will graph slower. And my calculator is old. So it's going to graph slower than most of yours. What I do, you don't have to do, but what I typically do is I go, how far apart are these two numbers? And divide by 10. It's just easy. Or you could divide by 5, but it's just easier to divide by 10. It's just a me thing. And now I'm going to hit graph. And I'm going to have a much nicer looking graph. There. That is the entire graph. This thing shoots up forever, shoots down forever after that. That's the entire graph. Yes, Zachary. Why did I change the window? Because if you here was the standard window. That's zoom 6. I can't see the top of the graph, so I don't know where the maximum is. And it's hard to see behavior. Like, it's just nicer to spread the graph out. So for window, it just made it a nicer picture left and right to shrink the x-axis and stretch the y-axis so I could see everything. See it thinking its way through that graph? If I wanted to kill the process, I would try to turn the calculator off. Second on, we'll stop it in its tracks. Okay? Which is beneficial for really, really complex graphs if you know you had a bad window. Anyway, we need to sketch this thing. And I can only see for sure what one of the x-intercepts is. One of the x-intercepts is at 0. I know that for a fact because x is a GCF. So I know for a fact it goes through 0, 0. Everything else, I don't know exactly where they are. And it's time for us to learn how to find where they are. Why did I do 6 for the intervals? No, that was on the y-axis. And I'm not even going to really care about the y-axis, I'm going to be honest with you. I'm just going to find those numbers, and I'm just going to, since it's just a sketch, what we care most about is the x-axis. That one's big time important. Okay? But no, you're right. That is 6, 12, 18, whatever, you know. Okay, we need to know where our other two solutions are. I need to know where that x-intercept is and that x-intercept is. There are two options. I prefer the option that's really only beneficial if you have a graphing calculator that's in color like mine. So if you have one of the thick ones that's not in color, then this method will not work well for you. I'll show you that one in just a second. On this graph, when you're on the y-axis, when you're on the x-axis, I said the wrong one. When you're on this x-axis, what does y equal? 0. So I'm going to go to y equals, and I'm going to type 0. And then I'm going to hit graph. If you have a black and white calculator, you will not see that it just put a line on the x-axis. But you can see on my screen up there that my x-axis turned red. Okay, don't worry, I'll show you the black and white. Yes?
Just straight up just type in 0?
Yeah. Y equals 0. That is the for y equals for y2. Scroll down and type 0. So there we go. This calculator can calculate where the intersections are. And you see this blue command right here that says calc? It's in there. In order to get these blue commands to work, you have to hit the blue button. Second, and then hit the trace button. Second trace takes you to the calculate menu. Since I have two different graphs on my screen and I'm looking for their intersections, I could do the command for intersect, which is the number 5. That was my phone. That was my phone. So anyway, press 5. That's right, I have Snapchat friends. Anyway, only if you can find me. So anyway, the calculator is going to prompt you. It has questions for, yes? Second trace, because we're going to the calculate menu, okay? And then I hit intersect, so 5. Okay. Anyway, notice the prompt right here. It says first curve, question mark. How many graphs did I graph? Only 2 of them, which means I'm guaranteed that that is one of them that I'm interested in. So I hit enter for yes. And it says, is this the other one? Notice the cursor didn't move. That's because it always starts at 0, 0. But trust me when I say, if these 2 graphs didn't intersect right there, it would have moved to the other curve. But I can just hit enter for yes again, because there's only 2 graphs. Now it says, why don't you take a guess where one of the solutions is? So I'm just going to scroll to the left. There's one right around there, and I'm going to hit enter. And it gives me my exact solution at negative 1.194. That's almost negative 2. Then you used the calculator wrong. Did you do second, trace, intersect?
Yes.
First curve, second curve, and guessed over by the answer?
Yes. It's 1.136.
No, you typed your equation wrong then. You missed something somewhere.
I didn't.
Let me see the calculator. It's exactly the same as mine.
Oh.
You didn't do second, you didn't do first curve, second curve, guess. You probably forgot to hit enter at the guess at the end. So we saw that one was almost, wait, what was it? Crap. Oh man, I put mine close to 1.9 by accident. That was supposed to be 1.19. Well, I'll just, there. Okay, picture not drawn to scale. Let's say it like that. Sorry. Anyway, let's find this other one over here. You can see it's just a little bit past 2. Second trace, 5. Yes, yes, by enter, enter, because there's only 2 graphs. And then I just scroll all over to the other solution. And I take a guess by hitting enter. And you see 2.07 actually. If you round it to 3 decimals, you get 2.07. Okay. Oh, crap. Was that black instead of blue? It was. I'm bad at this. All right. Now we're trying to still get good pictures. We want to know where this bump is and where this bump is. Before I go finding those bumps, though, allow me to show you how to find x-intercepts when you don't have a color calculator because, I mean, it'll still work, but it'll kind of be tough to realize that that's what happened. It can also calculate zeros. Second trace 0 is command 2. Notice, though, that the instructions from it have changed. Left bound means get to the left side of a solution. Hit enter. Right bound means get to the right side of a solution. Hit enter. Guess means go between the 2 vertical bars. And hit enter. And you will see I got negative 1.194 again. Yes?
So just using the 2 lines always better than if you have a color calculator?
Nope. It's not that it's always better. I just find it to be a little bit faster because I've memorized second trace 5, yes, yes, scroll. It just becomes something that you use often. But I'll tell you, though, I didn't do that until I had a color calculator. Okay. Now, this calculator can also calculate maximums and minimums. but it does it in a very similar fashion to what you just saw me do. Let's find a minimum. Second trace, minimum is command 3. It says get to the left of the minimum. Hit enter. Get to the right of the minimum. Hit enter. Get in between those two vertical lines. Hit enter. So it's at like almost -6. Almost -6. Yeah.
Why does it ask you to guess before it tells you?
Why does it ask you to guess before it tells you? Because there could be more than one minimum in that zone. And it wants to know specifically which one you're looking at. So the programmers made sure they took away your ability to accidentally have two minimums in one place by saying, get close to the one you care about. Usually there's only one there, right? But that's why. Okay. I'm just going to do this. Picture not drawn to scale. And I'm going to record this coordinate over here. This coordinate was at -0.688, comma, -5.966. That's where that point was. And I believe I did my minimums in orange last time. I'll just write min underneath it, even though it didn't ask me to. Yes?
How accurate do the decimals?
3 decimals for AP always.
No, I mean, like, how accurate does it have to be? It's, like, for example, multiple choice.
It has to be 3 decimals accurate.
Okay.
All decimals go to 3. You always need to go to 3 decimals. So you look at the 4th number and then round the 3rd one. That's it.
I know. I'm not going to say like 2.07. I'm not doing that. Or,
2.07.
like for a point.
Let me see it.
No,
I need. There's something wrong on the calculator. If your calculator did not give you 2.07 for this x, it's typed in wrong or you're not finding it right. I'll pause the video, okay?
Are you sure?
Yes, let me see it. Okay, problem solved. All right, now let's find the maximum the same way. But instead of doing second trace minimum, you do second trace maximum, which is command 4. Again, go to the left, hit enter. Go to the right, hit enter. Go between them, hit enter. There's your maximum. It's like up here. Picture not drawn to scale. Okay? Let's write down its coordinates. 1.458, comma, 31.409. And then I'm going to sketch my curve. There. So in this one example, we learned how to find maximums, minimums, and zeros in one example. Everything's through second trace. At this point, now we just do increasing and decreasing, and we'll talk about some major connections between everything. On the previous page, I shaded my increasing in green, did I not? Yes. I'm going to do the same thing here. Just because, why not? Continuity's sake. There we go. That was increasing. Remember, the x values. So we are increasing from -0.688, comma, and stopping decreasing at 1.458. You decrease on the rest of the domain. So decrease all of this, decrease all of this. I just realized that this says that's a positive 1.19. It's supposed to be negative. I just noticed. Someone watching the video might be screaming at their monitor forever. Anyway, we decreased from -infinity to this x value right here at this minimum, -0.688. And then it also decreases after the maximum. Oh, supposed to be brackets on increasing, decreasing. I hate that, but there it is. That was after 1.458. So then what is the connection between increasing, decreasing, and extrema? That is the question. What's the relationship? Well, every time a graph changes between increasing and decreasing at a point, that point will be a maximum or a minimum. It's called a turning point because of that, because it changed your behavior. But it has to be at a point. Can't be at an asymptote or anything like that. It has to be an actual point. So at a relative maximum, at a relative minimum, extreme values, extrema, will always be places where we change between increasing and decreasing. As long as it's not an endpoint, I should say. Extrema will always be the point where we change between increasing and decreasing as long as they're not an endpoint, because that's just an endpoint. But there's more to it than that. There's more to realize. There's more to understand. We will always find a minimum at a point where the graph stops decreasing and starts increasing. We will always find a maximum at a point where the graph stops increasing and starts decreasing. And that should make perfect sense. You know, if you're going to change between going down and going up, clearly there was a low point. And if you're going to change from going up to going down, there was clearly a high point. And then, last period, Barry Wimbish said something highly intelligent that's not even in the notes. Would anybody care to make another connection that'll always be true about maximums, minimums, and things that we have talked about so far? Ideas. I'm just going to try to give a couple people. London, give me an idea. Has to do with concavity. You will always find a minimum in a zone that is concave up. Every minimum, as long as it's not an endpoint, is in a concave up zone. Every maximum will end up being in a concave down zone. Always. They don't have a choice. And it's not in the notes, but that's the kind of thing where you understand it must be true. Seth, is that what you were going to say? Something along those lines? Were you going to say something different that's highly intelligent?
I was going to say that the rate of change is constant.
Ooh, and yes, and that is absolutely true as well. Because it's a turning point, because we go between a negative and positive rate of change, the turning point will always be a constant point. It's not a constant interval, but it'll always be a constant point, where at that one place in space, our instantaneous rate of change is 0 at turning points. They're also called stationary points because of that. But that's a calculus thing. Man, big old juicy brains floating around in here. Okay, we are finished with the graphing calculator now. I just wanted you to know how to do those things. You need to be able to find zeros, also intersections between graphs. You need to be able to find relative extrema, maximums and minimums. Between every two distinct real zeros of a non-constant polynomial function. Okay, how about regular words? Between every two different real answers of a spaghetti graph, there must be, and this goes to do with Max, the question you asked, there must be at least one x value that corresponds to a maximum or minimum. It doesn't have to be only one. That's why the calculator makes you take a guess. Okay. So between any two different real solutions, x-intercepts, there will always be an extreme value, at least one. Always. You don't have a choice. Because how are you going to leave the axis and come back to the axis unless you turned, right? Yes? What if it's a bounce? So if it bounces, then at that x-intercept, they're not distinct, different answers. They're a repeated answer at a bounce. And that's why they had to put the word distinct in there. It's a good question. But if you think about it, if it bounced and came back, then clearly there was an extreme value between there. because now we have two different values. Yep. So here we have this polynomial, piece of spaghetti. It goes right here. It happens to have very nice, x-intercepts. So the real zeros are their parity. We got one right here at -3. We got one right here at 0. And we got one right here at 4. Part C says to identify local extreme values. All three of those are maximums. No, they're not. What am I smoking? The one in the middle is a maximum. The graph was attempted to be manipulated so that the extreme values landed at pretty places. Let's just pretend they did so we don't have to pick up the calculator and do second trace minimums. Okay? Unless you want me to. You know what? Let's just do it. We might as well. We might as well. Let me go into y equals. Let me clear it out. And we're going to type what we see there. 0.15. You don't need the leading zero. X raised to the 4th minus 0.15 x raised to the 3rd minus 1.8 x squared. So we see the graph bounces off x equals 0. And that's because there's x squared as a GCF. And you could use zoom 6, or you could just, which is the standard 10 in all 4 directions, or you could just adjust the window from x's go from negative, 6 to +7, and y's go from -10 to +7, but who cares? Zoom 6 will work just fine. Zoom 6, the standard zoom. Because at this point, we're just hunting for the minimum and the maximum. Well, we know where the maximum is. It's at 0, 0. So we're just hunting for the two minimums. Second trace minimum. Second trace 3. Go to the left of where the minimum occurs. Go to the right of the minimum. Get in between. Boom. At -2.103, that is where I'm going to find this minimum. It says state the x value where it occurs. We don't actually care about the y. And then lastly, this minimum, and we'll have to call the video there. Second trace minimum. Enter, enter, answer. 2.853. That's going to do it, nerds. Appreciate you.